Let us now discuss about interprocess communication. As you know, there are a lot of processes in operating system, and those processes are assigned to complete some tasks, and to complete those tasks, those processes needs to communicate with each other among themselves. Without communicating with each other or without communicating with the operating system, those processes actually doesn't do or cannot do any effective work or cannot complete all kinds of tasks. So the processes needs to communicate among themselves, and this communication is named as, or we call it as, interprocess communication. So basically processes in the system are of two kinds in terms of communication. Some processes are independent and some processes are cooperating. So what are the independent processes? Independent process cannot affect or be affected by other process. I mean, they are lonely processes in the operating system. They doesn't affect anyone and they are not affected by any other process also. And the cooperating processes, they can affect other process or can be affected by other process. Okay, so in terms of communication, so there are two types of processes, and here we will discuss about the cooperating processes, because only cooperating processes actually communicate among themselves, right? They do the interprocess communication. So process cooperation is very much needed in the operating system. Why? The first one is the information sharing. If we think about the data that are stored in the operating system, many processes may need the same information. Okay, right? Say for example, if you run several software in your computer, you may find some information that are very common to all of this. Maybe if you use the Google Chrome and Adobe Reader both at the same time, they are different type of programs, or we can say they actually execute different type of processes, but somehow you may find that they do share some information. I mean, some data are same in the Adobe Reader as well as in your Google Chrome. Maybe those information is about user information. So information sharing is very much needed task in the operating system, and to share information among the processes needs to be cooperative process. Then comes computational speed up. So for example, if you want to speed up the calculation, maybe a big calculation which takes time, so if the processes are cooperating, then you can distribute the computational task among several processes, and in this way you can actually speed up the computation or the calculation. Then modularity. If you think about some systems, and then whenever you actually implement some system, and the basic idea is to make the system modular. I mean, you will create separate modulars first, and all those modules all together will actually make the system. So to achieve modularity in the system, there should be the modules or the processes needs to communicate with each other, right? So here also process communication is needed for modularity, and also for convenience. For say some user may use Google Chrome or video player or Adobe Reader, music player, all of these at the same time, right? So to communicate among all these processes that the user is currently executing, then there should be a medium or a technique to communicate among those. for convenience of use. So for convenience of use, process cooperation is also needed in the operating system. So from overall discussion, we can say that cooperating processes are very much needed in the operating system, or in modern operating system. All the processes are communicated because everything is linked, everything is connected, right? So data are shared among various softwares. So without the process cooperation, it is not at all possible. So interprocess communication, or IPC, is a mechanism to exchange data and information among processes. So we have discussed, or we have came to the conclusion that process communication is important, but how this communication will happen? So IPC is a mechanism that will actually do this task, this communication task among the processes. So there are mainly two fundamental model of IPC. The first one is the shared memory, and the second one is the message passing. So what are the differences between these two models? So if we think about the message passing, this is the example of message passing. So see, there's two process A and process B, and these two processes wants to communicate with each other. So in message passing system, how they actually communicate? They actually send messages to each other. How? In this model, there will be a queue. This queue is a message queue, and all the messages are stored here. Okay. So if process A wants to send a message to process B, what it will do? It will send a message, or it will store a message in this message queue, and in this message, process A will mention that this message is for process B. And when process B enters into this queue and searches if there's any message for him, it will find that this process was sent to him, was meant for him. So process B will get these messages. So in this way, actually message passing works. And to create this message queue, to send message and to receive message, a kernel intervention is very much necessary, because using the kernel or some system calls, actually this thing happens. Sending message and reading message. And now if we think about the shared memory system, in shared memory system there is no message, or there is no message queue, but there's a space. That space is shared among all the processes. So for example, if process A and B wants to communicate, process A will just send some data or information, or store some information in this shared memory, and process B will directly access that. Process B actually directly can see the data, the shared data from this location, right? So in this technique, or in this model, the process A and process B does not need to use any system call, or doesn't need to use kernel to store data here and to read data from here. Okay, so that is why actually shared memory actually works faster than the message passing system, because in message passing system all the processes needs kernel intervention to read and send message, but in the shared memory they don't need it. So let us now see an example of shared memory system to solve a problem. So the problem is the producer-consumer problem. What is the producer-consumer problem? In this problem, actually the producer produces products for the consumers, and consumer consume products that is provided by the producer. So here what happens, this is the shared space or shared memory, you can say, and this shared space is actually shared among the producer and the consumer. So what actually happens here, the producer actually produces items and those items are put here, and consumer actually collects or consumes items from this space. So this is called the producer consumer problem, and this problem actually is solved by this shared space. And you can think about this shared space as the shelves in the super shop or any shop. So the producer or the seller actually keeps the products in the shelves, and consumers or the customers actually collects the items from the shelves, right? So the shelves are the shared space, and in these shelves the producer produces until the common space is filled or full. So if the common shared space is full, the producer will not produce any more new item and it waits to get it empty, right? And the consumer actually consumes from here if he finds any item here. I mean, if the shared space is empty, the consumer cannot consume anything, but if there is item in the shared space, the consumer can consume. So this is the scenario for the producer consumer problem. So if you think about the solution, this is the code for the producer. The producer will produce item until the buffer is full, right? And consumer will consume item until the buffer is empty. Okay, so let us focus on the producer. So what will producer do? Producer will check if there is empty space in the buffer. If there is any empty space, then it will produce new item. So here we use actually two variables, one is in and another is out. So in actually represents the next free position in the buffer, and out represents the first full position in the buffer that can be consumed. So in the while loop, if you go through the code, you will find it very easy, but in the while loop you will find that this is the condition to check. If in plus 1 mod buffer size is out, I mean if the next position of the buffer is the first position, I mean in this case actually if the in value here, the buffer size is 7, right? There are 7 positions in the buffer, and currently now value of in is 6. I mean this is the next free position, and out is 0. Why? Because in the 0 location there is the first item that can be consumed. So if we follow this code or follow this condition, that is in plus 1, that is 6 plus 1, 7, mod buffer size, that is 7, is it equals to out? So if it is equals to out, then it does nothing. I mean it considers that the buffer is full. Actually this is not a perfect solution. So in this solution it is assumed that if there are n-1 items in the buffer, then the buffer is full. It is assumed here. So the condition is written in such a way that if there are n-1 item in the buffer, then the buffer will be full, the producer will not produce anything. See, the producer does nothing. But it is, if it is not, I mean if there are less than n-1 item in the buffer, then the producer will produce an item and the item will be placed in the next free position, and then in will be increased by 1. So this is the producer side code. And if you think about this scenario, see, in plus 1 is here 6, 6 mod 7 is not equals to out equals to 0. So 6 mod 7 is not equals to 0. So that is why this while condition is not satisfied. That is why this two line will be executed. and a new item will be placed in this fifth position, I mean fifth index of the buffer. Okay. Now if we think about the consumer, we will see that if the buffer is empty, then consumer has nothing to do, because the consumer cannot consume anything. Okay, so our while loop condition is if in equals to out, I mean if both are 0, that means the buffer is empty and the consumer does nothing. See, do nothing. But if it is not, if in and out is not equal in this scenario, then what the consumer will do? The consumer will actually consume one item. Which one the consumer will consume? This one, the out value. What the out represents? 0. So it will go to the index number 0 and it will consume this item. Okay, see this one, and then out will be increased to 1. That will be this item. So in the next time the consumer calls, then the item from here will be consumed. In the next time this item will be consumed. So in this way it will actually go on. So then again I'm saying that this is one solution to use a buffer, or we can say a shared space among the producer and consumer to synchronize among them. But this is not the perfect solution. A perfect solution is available, and you will see the best solution later in this course. Okay, so let us now go in details with message passing system. So if process P and Q want to communicate, they must send messages to and receive messages from each other. As we have seen earlier, message passing is all about sending and receiving messages. So there should be a communication link between P and Q, because without a communication link, the data or the communication cannot happen, right? So this is the scenario that P actually sends a message, that is M2, and Q receives the message M2 via a function call, that is receive function call, and P sends the message using the function send. So message passing system is actually useful for exchanging a small amount of data. If the message size is huge, then message passing system is not recommended. In that case we actually use shared memory system. And message passing system is more suitable for distributed system, where the process they are actually are situated in different location. So in that case, in that scenario, message passing system actually works better than the shared memory system.